everyone, and welcome back to another video. So today we're going to be solving the LeetCode question, last stone weight. Alright, so in this question we're going to be given an array of integers called stones, where stones I is the weight of the ith stone. So we're going to be playing a game, and we take the two heaviest stones and we smash them together. So if the two stones have the same weight, then both of the stones are going to be destroyed. But if they do not have the same weight, so let's say one has a weight of 10 and one has a weight of 5, then in that case, we're going to smash them and we're going to have a new stone with a weight of 5. So the remainder is going to be added, right? So our goal here is at the end of the game, there is at most one stone left, and we have to return the weight of the last remaining stone. And if there are no stones left, we're going to return 0. So let's actually quickly look at an example. So over here we have these stones and these are the weights. And the first thing, just to make it simple, is we want to get the two largest numbers. So a simple way to do that is just to sort the array, right? So let's sort it, and we're going to get 7, oh sorry, that would be 8 first. So that would be 8, 7, 4, 2, 1, 1, right? Perfect. Now let's take the largest two numbers, 8 and 7. Now in this case, when you smash them, we would get a resultant rock of weight 1. So let's add that rock. And now we're going to have the remaining, it's going to stay as it is. All right, perfect. So now we've got to sort it again because we want to get the other two maximum values. Now this is one pass. So we're going to keep doing this until we have at most one stone in our array, right? So now let's do it. So we've got to sort the array first. That is going to be 4, 2, 1, 1, 1. Perfect. Now we take the largest two numbers, 4 and 2, and when you smash them, you get a resultant weight of 2. So that's 2, 1, 1, 1. Perfect. Now we take now again, in this case, we had to sort it again because, well, in this case, it is sorted, but it's not always guaranteed. So you sort it, in this case it is, take the next two largest numbers, 2 and 1, and that is going to give us, when you smash them, we get a resultant weight of 1. So that's 1, 1, 1. Perfect. Now we sort it again. Now these two have the same weight. So now both the stones are going to get destroyed. Now finally, we're only going to have one stone left, and at this point we stop. And this is the value we're going to return. This is the weight of the last remaining stone. So now this could actually be one of our solutions, where each time we sort the array and keep doing this until we actually get the up to one stone at the ending. Now a problem with this is each time we have to perform a sort operation. Now, this could actually end up being very exhaustive, and performing a lot of these sort operations is not very efficient. So instead, let's try to think of some sort of data structure that we could possibly use that still kind of gives us the largest two elements, but it's a lot more efficient. So one we could think about is using a binary search tree. Now, a problem with this is based on how the binary search tree is made, it is just as efficient in getting the largest number specifically. So a badly made binary search tree is just going to be as good as big O of n to search an element, right? That is not the best option. But when it comes to this, we have a very specific thing or data structure that we could use called a max heap. So I will just explain what a heap is very quickly. And in a heap, you could have a max heap or a min heap. And I'll just be showing you what a max heap is. So in very simple terms, you have a root term, right? And this root term is guaranteed to be the largest term that exists. In other words, all of the children are going to be less than or equal to the root term. So the root term is the largest, and all the children are guaranteed to be less than or equal to, right? Now, another really cool property of a heap is the fact that when you create a heap, so let me just show you. So let's say I have a value here. Then I would always create it in such a way that I want to have a full binary tree, right? So that all the levels are almost equal with a maximum difference of 1. So in this case, I would then add a node over here, then I would add a node over here, and so on and so forth, right? So this is the pattern I am going to be following. And the reason for this is that I get a full binary tree, which decreases the search time as well. Now, just to go in more details on how this would actually work is each time I'm going to insert a node, I'm going to first check, is this node less than or equal to the root? And the reason for that is I want to keep holding this property true. Now, if that is not the case, what I'm going to do is I'm going to swap the values of these two nodes. And I'm going to iteratively keep doing that, right? So let's say this value is greater than this value. Then I'm going to swap these values as well. And again, the entire reason for this is that each root is the greatest value with respect to all of its children. Now, this is going to be the data structure we use. Now, we could implement this from scratch, but instead I'll just show you how to use it with an inbuilt Python library. So let's just look at how the code is going to look like. Alright, so what I want to do is show you how this works step by step, so it's pretty easy to understand how HeapQ works. So just to kind of show you the first thing, I'm going to print out stones, and then I am going to heapify it. So what does that exactly mean? So I have this array stones, and now what I want to do is I want to construct it as a heap tree. And to do that, I can use the heapify function from HeapQ. So heapify and pass in stones. Now I'm going to print stones and let's see what the result looks like. Okay, so let's run it. Just to be sure, whatever it's getting printed over here is going to be the tree representation, right? But regardless, we can notice that this is actually in ascending order. This is not a max heap. Instead, this is a minimum heap, right? So instead of the root being the largest value, the root is the smallest value. Now, HeapQ by default doesn't have a way that we can change this. So a simple workaround we have is we can just treat them as negative numbers, right? So that way we basically get it in a descending order if we look at the absolute values. So let me just run this. And yeah, as you can see, we got the root being the largest value if you look at it as an absolute value. So 8 and 7 and so on and so forth, right? So this is what we get. So now each time, so let's look at what the next step is. So the next step would be to get the maximum value. So to do this, the function that we actually use is something called a heap pop. And a heap pop is going to get us the maximum element in this case. This case. So we get the absolute value of that because we're storing it as negatives. Now we got the maximum value, and now we want to get the second maximum value, the second largest value. So now all we had to do is we got to pop again, right? So this is going to now give us the second largest value. So now we got the largest two values. So let's take a look at them, max 1 and max 2. So now we got the two largest values. So let's just, okay, so 8 and 7, perfect. That is what we were expecting. Now, how exactly are we going to handle this? So now in this case, what we want to do is we want to keep track of what the remaining value is. So the remaining value is going to be max 1 because max 1 is greater than or equal to max 2. So max 1 minus max 2. Now this is our remaining value. Now our remaining value can be 0. But if it is not 0, so if remaining is not equal to 0, then in that case what we're going to do is we're going to add this value back to our heap, right? So the way we do that, and when we add this value back to the heap, it itself is going to get sorted in the heap. So this over here is called a heap push. So heap push, and we want to give where we're pushing it to. So we're pushing it to stones, and what we're pushing has a value of remaining, right? So that is going to be it. So that is going to be a full iteration. So over here, I'm going to print stones just so you can see what a full iteration looks like. So yeah, so perfect. So we sorted it. We got the largest two numbers, 8 and 7. And now in this case, what we did is we pushed it back. So one small mistake is when we push it back, we got to push the negative value. So that's going to be negative remaining. Cool. So this is going to be exactly what we want to do. So now instead, so this is going to be one pass. So how can we actually do the same thing but for several passes? So that's actually going to be really simple. We're just going to wrap it inside of a while loop. So we're going to first do this, then we're going to heapify it, and the rest is going to be in a while loop. So while the length of stones is less than 1. So while the length of stones is less than 1, we're going to keep staying in this while loop. So the first thing we do is we get the maximum values. So we get max 1 and max 2, and then we get the remaining value. Now, if the remaining value is not equal to 0, we push that value inside. So that is going to be the entire thing. Now at the ending, if we exit the while loop, that means we have a length of less than or equal to 1. So either 1 or 0. So we're going to return 0 if not stones. So if stones is empty, we return 0. Else, we're going to return whatever the last value is. And that is the same as doing a heap pop. So heap pop stones. And again, remember, we want to take the absolute value. So let's submit this solution over here. And as you can see, our submission has been accepted. So thanks a lot for watching, guys, and do let me know if you have any questions. Thank you.